Hi everyone. In this presentation, I'm going to talk about our work, which synthesizes trigger action programs from traces of behavior. In a smart home, we may want to have automation such as turning on the light when entering the room. To support users developing programs for such automation, there are several approaches. For example, we can let users write programs. A very easy to understand and popular syntax for end-user programming is trigger action program in the format of if this, then that. For example, if door becomes closed, turn lamp off. However, handling complicated tasks can become confusing to end users. Another example is trying to learn programs that can mimic users' behaviors in the history, which we will refer to as trace. A trace is a collection of all events happened in history, together with their timestamps. However, only relying on the trace can cause some issues. Users' behavior in the trace doesn't always represent users' intended automation. Say, a user wants to turn off the lamp when leaving the office. In her trace, she will first turn off the lamp, and then leave the office, as the switch is located inside the office. However, in the ideal automation, she might actually want to make sure she has left the office before automatically turning off the light. We see the order of two events switches. The intended automation can be quite different from the trace. Moreover, even from the same trace, we can't learn a general best program for all users. Different users might have different preferred programs because of their personality or device usage. To summarize, previous trace learners try to learn the best rule from users' behavior, which we think is not effective. There might be many different best rules depending on the criteria, like automating most manual actions or causing fewest false positives or others. Or maybe none of these criteria is what they want. Our solution for finding what the user really wants takes two steps. First, we use formal methods to synthesize all the rules that can automate some manual actions, not necessarily the best. Then, we carefully cluster, rank, and visualize these rules to help users find the rules they want quickly. Specifically, to use Trace2TAP, the user can first choose an action they want to automate, say, turn the lamp off. Trace2TAP then identifies all instances where this manual action occurred in the past. It then exhaustively looks for all the rules with this format that can automate at least a certain proportion of manual action instances in the trace. This is mapped into a symbolic constraint solving problem by us and gets solved by a SMT solver. After many rule candidates are synthesized, we need to think about how to present them to the user. Some rules are very similar, like these two, handling the case when the user goes home. We probably want to present them in a ranked way. Users would likely only choose one of them. While some rules are clearly handling different contexts, like these two, it does not make sense to rank them. Based on context each rule would handle, we put rules into different clusters using a discrete version of k-means algorithm. Users can click to iterate through different clusters that each handles different contexts. Rules handling similar contexts are put into the same cluster and are ranked. Now, the user can easily pick a top rule from every cluster that she is interested in. Our tool also has many other features like debugging existing rules and visualizing rule effect that you can find in our paper. We installed smart devices in 7 participants' offices in our department and collected their behavior for months. Altogether, we installed 53 devices and collected more than 1 million events. We identified 18 target actions to be automated, such as turning on the table lamp. At the end of the study, we used Trace2TAP to synthesize rules and presented rules to participants. Trace2TAP worked very well. Participants were able to find desired rules for most of the actions to automate. Our clustering-based rule presentation is helpful, as the 32 rules participants selected were from 31 clusters, with a median rank of 2. The result also supported our claim that trace doesn't always correspond to users' preferred rules, and different users have different preferences. We are open sourcing our algorithm, our tool, and the anonymized data we collected in our user study. Please check out our paper and website for more information. Thank you.